Welcome back to another Calcoholic video. I'm Shahvosian, and today we're going to be looking at infinite sequences in series. So to start us off, let me ask us a review question. What are sequences? So hopefully you remember because it's a pre-calculus topic, but in case we don't, let me remind you. So let's say we have a list of numbers. It goes 1, then 2, then 4, then 8, and it continues onwards infinitely. We can assign each number in this list some a. So let's say the first one is a sub 0, then the second one is a sub 1, the third a sub second, and the fourth a sub 3. And that continues onwards. So this ellipse, heavy quotes, I'm saying, continues onwards for infinity amounts of a. And that's what that notation means. That's why I put it in red and I've put heavy quotes around it because that's not correct notation, but that's how I'm going to express it. So now let this be a sub n. And that's the notation that we're going to use to denote this sequence. Now, what if we wanted to express it algebraically? What does this mean, a sub n? Well, let's give it an algebraic expression in terms of n. And you'll see that's what I've done here. I've said that my sequence a sub n is equal to 2 to the power of n, such that my n is a positive integer. Right, because if it was negative, that wouldn't make sense here. We'd be fractions. So now, how do we verify that this is the correct algebraic expression for this sequence, this list of numbers? Let's go ahead and plug 0. If we go ahead and plug 0, we'll see that a sub 0 perfectly matches what's inside of my list for a sub 0. And a sub 1 similarly is also 2, and a sub 2 similarly is also 4. So we've made a correct algebraic expression for those numbers in that list. Now, what about this list of numbers here? We have 1, then a half, then a fourth, then an eighth, and it continues onwards infinitely. And let's do the same thing we did previously. Let's title this one as a sub 0, then title this one as a sub 1, and then continue onwards. Again, let's look at an algebraic representation of what's happening in this list. We'll see that we can represent the sequence as a sub n is equal to 2 to the power of negative n, such that the n's are in the element of the positive whole integers. Right, and you can verify this just by plugging in any value of n, and that will be the nth number in that sequence. All right, cool. So hopefully we remember what a sequence is, but how is a sequence any different from a series? Well, let's go and bring that sequence back. And now instead of just knowing what number is at what n, what if we wanted to add all of these numbers in the list? So what we've done is we've put the sigma operator on our sequence. And what that ends up doing is we're adding all the numbers in our sequence. So not just that they're in a list, but we're actually doing something with them. So that's what this notation here represents. We have n going from 0 to infinity of 2 to the power of n. And this is going to equal 1 plus 2 plus 4 plus 8, all until the infinitieth number, whatever it is. And a general form for an infinite series looks as follows, which makes sense. So now, what if we wanted to evaluate this sum? What is it equal to? Well, if we just look at what numbers we're adding together, we'll see we have 1, then plus 2, then plus 4, then plus 8. The numbers are getting larger, and they're always positive. So if we add up an infinite amount of positive numbers, and not only that, they're increasing as n increases, and of course this sum is going to diverge to infinity. But what about this sequence here? 2 to the power of negative n. What if we wanted to find its sum? What do? Well, let's recall our knowledge from pre-calculus. So if we have a series in any of these forms where we have an initial value of a sequence times a common ratio r raised to the nth power, then that sum is equal to that initial value of that sequence divided by the 1 minus the common ratio. And this is supposing that r is a real number such that the absolute value of r is less than 1. Now, if it's any other case, so that the absolute value of r is greater than 1, then this sum is going to be divergent, as we saw with like the first example, right? Where it was 1 plus 2 plus 4 plus 8 onwards. Of course, it's going to be divergent. We're adding infinitely growing positive numbers to each other. We're going to be diverging. So if we go ahead and plug in the numbers we have here, we're going to see that our infinite series here is equal to 2. And these type of series are actually a very specific kind. They're called geometric series. And I have it in blue here because it lays the foundation for all the other series that you're going to be looking at. So it's the same as the last page. So how do we know if a series converges or diverges? What if our series is not a geometric series? Is there any way we can know if it converges or diverges? And the answer is yes, but you have to test for convergence or divergence. There's no way to know with 100% certainty just by looking at something that is convergent or divergent. You have to test for it. So how might we rigorously test that this sum that we saw just by looking at it common sense was divergent? Well, you could obviously say that it's a divergent geometric series, or you can find the quote-unquote last term in the series. So if you take the limit as n approaches infinity for 2 to the power of n, this equals infinity. So at one point, we're literally adding an infinite number to itself an infinite amount of times. This is going to be a crazy large sum. So of course, it diverges. Now, what we've just done is called the nth term test for divergence. So for any series, evaluate the limit as n approaches infinity of the inner sequence. And if that limit equals 0, then the test is inconclusive. You don't know if the series diverges or if it converges. It's inconclusive. You have to work harder. But if you're lucky and it doesn't equal 0, then the series is divergent. And this means even if it's 0.000001, that small, it's still divergent, because if you have an infinite number of those really, really small numbers, you're still infinite. For example, if I had a grain of sand, but I added an infinite amount of those grains of sand, like I'm still gonna have infinite sand. Doesn't matter where I started from. So the only time that this test helps you out is if you're not 0, because you know for 100% certainty that your series is divergent. All right, well, what about this one here? The infinite series going from 1 to infinity of 1 divided by n. All right, well, let's try the nth term test for divergence, and we'll see that the limit as n approaches infinity of the inner sequence is 0. So our nth term test for divergence failed. It's inconclusive. We're not sure if it's convergent or divergent, so we have to work harder. So why don't we think outside the box a little bit, outside of what we learned in pre-calculus, and look at a plane here, a Cartesian, where I've kind of made my x-axis, the x equals n, so I'm saying the n-axis, x-axis the same. And on my y-axis, I'm plotting the values of my inner sequence for certain n. And then you also see this blue curve here. I've turned my same sequence into a continuous function. And now why don't I draw boxes here? And the areas of these boxes are going to represent the values of my sum. And then what you'll realize here is if these areas of these boxes are the sum, then quite clearly the integral of the curve f of x is less than the sum, right? The sum is an overestimate. It's a left point Riemann sum of this function. So we know that left point Riemann sum for a decreasing function, it's going to be greater than, it's going to be overestimate than the integral. So knowing this, if we just evaluate the integral, we can have some type of idea of how this sum is going to behave. And if we do that, we'll see that we'll get ln of t such that t tends to infinity, which is of course infinity. And so the claim we're making here is that this sum is larger than infinity. And of course, if something is greater than infinity, it's also infinite itself. So this series is divergent. Now, what is this series called? It's actually a very special series. It has a lot of historical significance, and it's called the harmonic series. So it fails the nth term test for divergence. It appears to be convergent, yet it still diverges. And this sum was very difficult for ancient mathematicians to prove. And for a long time, they thought it was convergent because it does look convergent, right? You're getting smaller and smaller. You would think that at some point, it wouldn't be getting any larger, but it's not. And we've just proved it. So they didn't know that until they kind of grew their calculus knowledge. And then now here we are. So what we've just done is called the integral test. If there exists a positive, continuous, weakly decreasing function of f, such that a sub n can be turned into some function of n, for all n greater than or equal to n, sorry, let me say that again. For all n greater than or equal to big N, then evaluate the integral from big N to infinity of f of x dx, where f of x is just our sequence, but we've replaced the dummy variable from n to x. So now if this integral is divergent, then our sum is divergent. And if it's convergent, then the sum is also convergent, right? And we just gave like an intuitive little graphic as to why that is. Okay, cool. Now let me ask you a random question. For what values of p is this sum convergent? And what values of p is it divergent? So we've inserted the parameter p into the harmonic series to kind of get a sense for some of its like sibling series. Well, if I do an integral test on the case where p was 1, I just have the harmonic series and we know it diverges. Well, what if p is less than 1? We'll also see it diverges because our integral would be a square root function, which at infinity is still infinity. Now, if p is greater than 1, we're going to get a rational function, and that is going to converge at infinity. So we have these two cases for p. If we have the sum going from 1 to infinity of 1 divided by n to the p, then we're converging as long as p is a real number and p is greater than 1. Now, in any other case, so if p is equal to 1 or p is less than 1, then we're going to diverge. So what does this mean about the harmonic series itself? It means that the harmonic series is on the cusp of convergence. If the p for the harmonic series was any larger than 1, literally 0.000001 larger, then it would be convergent. So yes, this is called the p series, fitting for the name because the parameter we put was p. And it says a series in the form from n equals 1 to infinity of 1 by n p converges if p is greater than 1, otherwise it diverges. All right, now recall that the harmonic series is divergent, right? You can prove it with the integral test, or you can prove it by the p series. But what about this one? This series where the sign is alternating at each term. So let's just map out the first few terms to kind of get a sense of what we're looking at. And we'll see we're going from 1, then we're subtracting a half, then adding a third, then subtracting a fourth. So what does this do towards infinity? Are we convergent or are we divergent? Well, remember that the harmonic series itself was on the cusp of convergence, meaning if we were any smaller, then it would be convergent. So the fact that we've subtracted out some terms from the harmonic series means that this alternating series version is convergent. But how can we prove it with math? That wasn't very rigorous. Well, we've produced the alternating series test. So for any alternating series, like the one we just saw, if you take the limit of the absolute value of what's under the summation operator, and it's equal to 0, then that implies that your whole sum converges conditionally. And let me just emphasize what converges conditionally means. Converges conditionally means that it only converges if it's an alternating series. Otherwise, it is not convergent, just like the harmonic series. All right, now let us look at another sum. We have the sum for going from 1 to infinity of 1 by n squared plus 2n plus 1. Now I'm going to put this function of our sequence, I'm just going to turn it into a function, and we're going to see that f of x is positive, it's continuous, and it's weakly decreasing for all x greater than or equal to 1. So if you wished, you could do an integral test on this, although I don't recommend it. So why don't we think a little harder about what we're given, the question we're given, and we'll see that 1 by n squared plus 2n plus 1 is always smaller than 1 by n squared, because what's in the denominator is larger, which means the output is going to be smaller. So it's smaller than 1 by n squared. And recall that 1 by n squared, its sum, its infinite series, is a convergent p series. So then just by comparing the two, we can tell that this sum that we have right here, n squared plus 2n plus 1, is also convergent. All right, so now what does this tell us for more abstract cases? Well, we can do a basic comparison test. So for any unknown series, compare it to a known series, and if that known series is convergent and somehow greater than the unknown series, then you know that your unknown series is convergent, and the vice versa is also true. So let's go ahead and look over here at a ratio between what we know was convergent and what kind of implications that has to the whole sum. So if we take a ratio of our unknown sequence and divide it by a sequence that we know produces a convergent series, then if this limit converges, then we can assume that the sum also converges. And it does. This equals 1. So we've also proved in another way that this is equal to 1. And this is also a comparison test, right? This is also a comparison test. We've compared to a known series, but we've done it in a different way, and that's why we give it a different name. This name is the limit comparison test. So for any series, for any known series, for any unknown series, compare it to a known series by evaluating this limit here, this ratio of your unknown by your known, and say it's equal some L. If that L is not 0, then your known and unknown series will converge and diverge together. If L is infinity and B sub and your known series diverges, then that implies that your unknown series also diverges. And there's so many of these that you can just by intuition and which sequence you know and which sequence you don't know. You can come up with way more than what's just on the screen, but these ones are the ones you're usually going to see. So that's why I've put it here. All right, now the ratio test. So I'm just going to throw this test there. I'm not going to kind of show how the thought process was because I want you to work with the test. So say you have a series. Let the limit as n approaches infinity for a sub n plus 1 over a sub n equal L. Now, if L is bounded between 0 and 1 and can also be 0, then the series converges, absolutely no questions asked. If L is greater than 1, then that implies that your series is divergent. Now, if it is equal to 1, your test was inconclusive. You don't know if it converges or you don't know if it diverges. So now why don't we try and work with this sum here? Don't use an integral test. Don't use a geometric series. Don't compare it to any P series. Just try and use the ratio test. And what you'll see here is, well, first what we're going to have to do is figure out what a sub n is, and it's pretty obviously the only thing under the summation, which is 1 over e to the n. So now if we work with that sequence, we'll see that that ratio is 1 by e. Now, what implications does this have? First of all, the reason why I didn't write any limits here is because 1 by e is not affected by n, so the limit would do nothing, so I just didn't even bother writing it. And what implications does this have? Well, because 1 by e is bounded between 0 and 1, then that implies that this infinite series converges absolutely. And it does, right? It's a geometric series with common ratio 1 by e, so it's less than 1, so it converges. But why don't we look at our work more carefully? The operations we've done to our original sequence would have been the same as taking the nth root of whatever is under the absolute value. So this is the same as taking the nth root of our sequence, which would give us also 1 divided by e. So this births kind of a new test, what we call the root test. So for any series, let the limit as n approach infinity of the absolute value of the nth root of a sub n, and let it equal L. And it follows the exact same conditions as the previous ratio test. And so there are questions where you see a sequence to a power of n, and automatically you should know that you have to take a root test, right? Because you're taking the nth root. It's going to simplify your sequence quite nicely. So what I want to do now is encourage you to watch the next video that's going to come after this, which is practice problems. So now that you know all the tests, you need to apply what you've learned. So in the next video, we're going to go over some practice problems. All right. Now, before you go over to that video, please subscribe, right? We work really hard on these videos, and it would mean a lot for you guys to subscribe, right? It's always good to know that people are watching these videos and they're actually helping people out, because that's the purpose of these at the end of the day. So please hit that subscribe button, like, and leave a comment. And that's it for today. So thank you.